is about playing a game rock paper scissors over an instant messaging platform. So part one asks you to see what problems people might run into if they use such a platform. Well, basically, an instant messenger works sequentially. So whenever Alice and Bob want to reveal their choices, one of them is going to see the other one's choice first, right? So for example, if Alice reveals her choice first, then Bob is going to see her choice before revealing his. So even if Bob was losing, for example, if Alice had chosen rock and Bob had chosen scissors, Bob sees that Alice chooses rock, so before sending his message to Alice, he can switch to papers, which would make the game, make Bob win, right? So this generally becomes like a game of being the last one to respond, which is not the same as rock paper scissors. So that's basically the problem that we run into. Now in part two, we are looking for a solution for this problem. Okay, so assume that we found a scheme using which Alice could commit to a choice without revealing that choice to Bob. Okay, then the way the game would proceed from then would be Alice and Bob each choose their choices and keep it private. Then Alice commits to her choice by sending something to Bob. Bob receives that thing, but there should be no way for Bob to basically extract Alice's choice from that thing. Okay, Bob also sends Alice a token, basically, which makes Bob commit to his choice, but Alice should not be able to use that token to find out what Bob's choice is. Okay, so how does a mechanism like this work? We are going to use RSA. Okay, so let's look at when Alice wants to commit to her choice. Alice has a private key and also a public key. Alice wants to send a message to Bob, right? Naturally, that message is going to be one of the three choices: rock, paper, and scissors. But obviously, Alice doesn't want to send the exact message to Bob, because that would reveal Alice's choice. So Alice should encrypt X before sending it to Bob. Now, if Alice were to use her private key, then we know that the inverse to encryption with private key is encryption with public key, right? So Bob knows Alice's public key, so he would be able to decrypt what Alice sent him, right? So we obviously don't want to do that. Now, how about Alice encrypting the message with her public key? So Alice is gonna encrypt X using her public key, and then Alice is gonna send this to Bob. Now, assuming that Bob doesn't know Alice's private key, Bob is presumably not able to figure out what X is, right? Okay, so far so good. But how is this a commitment for Alice? Alice could easily change her choice after even sending this message to Bob. Well, the thing is that after Bob also has committed to his choice, they can both reveal their plain choices. Okay, so for example, Alice can do so by sending the original X that she chose to Bob. Okay, now see what happens. If Alice sends her own choice to Bob, then all is good. But what if Alice tries to change her choice? For example, if she originally picked rock, but now she is trying to choose a different thing, like paper. Would Bob be able to figure out that Alice is cheating? Well, yes. The thing is that Bob has access to Alice's public key, right? So, when Bob receives Alice's true original choice, Bob can compute this whole thing, right? And then he can compare it to what Alice sent him first. If this was not the same thing that Alice sent Bob first, then Bob would know that Alice is cheating, right? So this creates a mechanism by which Alice is committing to something without Bob knowing that thing. And then whenever Alice decides to, Alice can prove to Bob that her choice was something. And Bob would be able to know if Alice is cheating or not, right? So with all of this being said, the mechanism works like this. Alice and Bob both pick their own choices. So Alice is going to choose X, Bob is going to choose Y. Then Alice is going to encrypt X with her public key. So it's going to be encrypt X with Alice's public key. And then Alice is going to send this to Bob. Bob is going to do the same thing, but with with Y and his own public key. So Bob is going to encrypt Y with Bob's public key. And Bob is going to send this to Alice. Okay? Now Bob has something from Alice and Alice has something from Bob, but neither one is able to decrypt that thing to figure out the other one's choice, right? So for example, if Bob here received Alice's message first, he wouldn't know what it is in order to cheat and change his choice before sending this to Alice. Okay, so far so good. When both persons have received the message from the other one, then they reveal their own choices. So Alice would send X to Bob and Bob would send Y to Alice. Now each person has a way of figuring out whether the other person was cheating or not. Bob would simply plug X into the encryption function with Alice's public key. So Bob would be able to compute this now that he has access to X. And then he can compare what he gets with the original thing that Alice sent him. If they're not equal, that means that Alice is cheating. Alice can do the same and figure out whether Bob is cheating or not. And then they both know what each one's choices were. And so they can decide the fate of the game. Now, there is a slight complication here. The thing is that here we only have 3 choices, right? So when Alice picks a choice, rock, paper, or scissors, and sends the encrypted choice to Bob, So Alice is going to send X encryption of X with Alice's public key. To Bob. This X is coming from a set which only has 3 elements, right? So this whole thing can have at most 3 different values, right? So Bob could have pre-computed this thing for all of the choices, rock, paper, and scissors, and then just by looking at this and comparing this thing to all of the 3 pre-computed choices, Bob can figure out whether Alice's choice is rock, paper, or scissors. That's basically a way for Bob to break the system. Now, what can we do to fix this problem? Well, the thing is that Alice doesn't really need to send only rock, paper, or scissors. Alice can basically append something arbitrary, like the time of the day, or like some random bits to her message, in order to make this X a little bit more complicated. So Alice is going to send a message which is longer. So for example, it's going to be rock and then some arbitrarily long number like 1246 09 something. And then Alice is going to encrypt this whole thing with her public key, and then she's going to send that to Bob. Okay, now Bob has no way of having pre-computed the encrypted message for all values that look like this, right? So this fixes the problem, but what about the other step where Alice is going to reveal her choice and Bob is going to check that Alice is not cheating? Well, here's the thing. Alice has to remember the arbitrary message that was appended to her choice. So Alice is going to remember not only that she chose rock, but also that she appended it by 124609 something. Okay, now when it's time to reveal choices, Alice doesn't only send not only sends rock to Bob, she also sends this whole arbitrary thing. So Alice sends this whole message to Bob without encrypting it, and now Bob can compute this function encryption for the plain message that Alice sent her, and then check the encrypted message to see whether Alice is cheating or not. That would basically strengthen the security of the system.